Hello and welcome. We're going to talk in this lecture about matrices and linear transformations in R2. Now, linear transformations are easily the most important thing you'll ever study in linear algebra. Matrices, of course, are very closely associated with linear transformations. We're going to see all that in this lecture. Okay, so first of all, let me introduce a matrix as a grid of numbers, and this is something you might be familiar with. You might have seen it earlier. We have also seen it earlier. Let's just quickly define that and get it out of the way. So when I'm thinking of a 2 by 2 matrix, I'm going to put a 2 by 2 grid of numbers and put this sort of long square brackets on either side, and this becomes a matrix. So I have A11 in the first position in the first row. So there are two columns and 2 rows. In the first row there are 2 numbers A11, A12. Second row there are 2 numbers, first column, second column, etc. It's just a grid arrangement. The 2 rows are A11, A12, A21, A22. The 2 columns are A11, A21 in this direction, right? A12, A22. Okay, so this is sort of like a a storage entity. If you don't put any other structure around it. For now, this is a way in which you can store two-dimensional data. Like for instance, image data is very commonly stored as a two-dimensional matrix. There's other data for which you need 2 dimensions. You may have a space dimension and a time dimension. Then you have to, you have to store 2-dimensional data. So a lot of 2-dimensional data matrices show up in many programs that you may write. Okay, so that's the grid of numbers view of a matrix. Okay. Now, the same grid of numbers, interestingly, also shows up in this matrix vector form of a linear equation. This is something we've seen in Math 1 as well. You have 2 linear equations and 2 variables. This is a very common, starting point for doing problem solving in general, right? So you have linear equations, linear variables. We use this method called elimination, and for elimination also, this matrix vector form of a linear equation is very useful. So how do we write it? Basically, we write this as a linear combination, one vector equation. 2 scalar equations become one vector equation. A linear combination of these 2 vectors, the 2 columns, so to speak, becomes C1, C2, right? A11, A21 and A12, A22. So you can write this as a matrix vector product. You write this matrix out here and the vector out here and define the product, right? A times V to be this linear combination. Now, is it really this kind of multiplication? Is it only for this linear equation, or does it have more meaning? We have not seen that very closely. We're going to do that shortly. But we have seen that this form helps us a lot in doing elimination, right? So we write A and B together, and then A and C together, right? C1, C2, and then we start eliminating and we get to the solution. Okay? So the matrix vector form is very useful for solving equations. So it seems like we have utility for the matrix, but where does it come from? Where does it really come from? Where does this vector product, vector matrix product come from? Okay, so all that has its root in linear transformations. We're going to see that in this lecture itself. Okay, so what are these linear transformations? Okay, so these are very important, and like I said, this is clearly the heart and soul of all of linear algebra. So you have to have a good understanding of what these are. Okay, so before we talk about linear transformations, let's first talk about transformations. What are transformations? Transformations are nothing but functions. Okay, right? So we've always been talking about functions. F of x takes f of x is a common way in which we write a function. X is a real number. F of x is a real number. It goes from reals to reals, right? So that's the function. So when we say transformation, we are thinking of something that goes from vector to vector. Okay, so here is a picture to keep in mind. So you have an R2 here, you have another R2 here, and a transformation T takes an input vector from, let's say, this R2. Both of them are the same in some sense, but anyway, just for convenience, we'll write it like this. From this R2, it takes this white colored vector and specifies a rule for going from U to this V, which is this, I've shown it conveniently in red color here, which I've shown also in this other R2. Of course, this V is also there in this R2, but just for convenience, to show that there is this transformation, you draw this long arrow and go from U to V. Of course, the T, for it to be a proper transformation, useful transformation, it needs to specify this for every U, okay, not just this point, for every point. I've just shown some 2 points. For example, maybe this one goes all the way here, this guy goes all the way here. Maybe these are a couple of examples. I mean, likewise, This capital T is a transformation if it specifies how every point goes to some point in R2. Okay, so it's like a function, but input is a vector, output is a vector. Okay, so this is a transformation in general. Okay, it looks like there is a wildly large number of transformation, and we may not be able to study it very easily. We can be a bit systematic about it, and it turns out these linear transformations are but particularly easy to study. Okay, before that, let's see a few examples. Okay, what are these transformations? Are there some easy, nice examples of transformation? We're going to start with some simple examples, and you'll see that those are very nice to deal with, and we'll slowly generalize from there. Okay, the first example of a very, very useful transformation is something called translation. Okay, so what happens in translation, right? So here is the description mathematically. So you see, you can write down the transformation as the equation, and you can also visualize it on this picture. In this picture, I've shown the R2, the two R2s I had in the previous one has sort of fused into one R2. I'm showing both the blue, white and the red in the same picture. So what does translation do? It takes the input and translates it, basically moves it to another point on the plane. Okay, so that is basically written as an equation. If you have T of u, then it takes u and then adds a constant a b vector to it, u plus ab. So x comma y goes to x plus a comma y plus b. Okay, so I hope this is clear to you. Translation is a very, very important and basic transformation in R2. So what happens to every other point? I've shown every other couple of other points here. This point goes to this point, this point goes to this point. Same thing would happen to any other point. So you can see why it's called a translation. No, it's got a moved from one starting point to ending point in the direction of AB to the magnitude of AB also. So in that same direction it has moved. Okay, so this is translation. Okay, and then the next very interesting transformation, very simple one, is scaling. Okay, so what is scaling? Scaling is easy to see. The equation itself is easy to write down. T of u is simply some alpha, alpha is a real number, some alpha times u. So you take the u, multiply it by alpha, you scale it by alpha. Okay, so what happens here on this picture in R2, my white is going to go to red. Okay, maybe the scaling factor is like 2, right? So this one is, so this and this are sort of equal, so maybe this is a factor of 2. So xy went to 2x dy, maybe, right? So that's something like that. So same thing would happen to every other point. If you had a point here, it would go in the same direction 2 times. This point here, same direction 2 times. So notice how scaling doesn't give you the same magnitude, right? So see here, every time when the initial point to final mood, you had the same magnitude. So here it will depend on the original magnitude. This one went much farther, this one went very close, right? So it's like that. So it's different transformations have different features. So scaling has a very different type of feel to it than translation. Another very interesting transformation is something called rotation. Okay, so what happens in rotation? We don't yet know enough to. I mean, it's not immediate what T of u is. You can write it down, but I prefer to think of it in polar coordinates. In polar coordinates, this T of u is very easy to think about. So u, instead of writing it in xy, if you write in r theta, rotation is very, very easy, right? Suppose u is r theta coordinates. What is T of u? R remains the same, theta becomes theta plus theta naught. So this is like anti-clockwise rotation by theta naught. Okay, so r comma theta plus theta naught. Okay, so I hope this is clear. So the same thing would happen everywhere. So what happens when you rotate? The magnitude doesn't change, but the direction changes by this angle theta naught. Same thing happens to every other point. A point here would rotate like this, point here would rotate like this. Okay, so this is what rotation does. Okay, so there's all sorts of transformations here, and you can imagine so many other things. You can do a mix of scaling, translation, rotation. You can do all sorts of things. So it looks like there is a big zoo of all possible transformations out there. And how do you study them systematically is an important question. So the first and basic transformation to consider, which we can easily study, is linear transformations, and that's what we're going to look at next. Okay, so this is linear transformation. So what makes a transformation linear? Okay, if you have a transformation T from R2 to R2, it is said to be linear if the two conditions here are satisfied. Notice this condition, it's written down in an equation, it's easy to parse. Okay, so what's happening here? So you have u1, u2, you take two vectors in R2. What am I doing in both sides of this equation? In the left hand side, I am adding u1 and u2 first and then applying t. Okay, I add u1 and u2 first and then apply t. I will get some vector here, no? That's okay, I'll get it. So what am I doing on the right hand side? I am applying t first to u1, I am applying t second to u2, and then after the application of t I am adding. Okay, so notice how these two operations are different, right? These need not be the same all the time. I will show you an example of one of the previous three transformation where this doesn't hold. Okay, so this is a condition that we are imposing on the linear transform on this transformation. Okay, so if it's linear only if it satisfies this condition. All transformations need not satisfy this kind of condition. Okay, so this is an important criteria. It's a nice criteria. It makes it linear. This t sort of distributes inside the addition operation, and it's a nice thing to have. Okay, look at the next one. Next one is also sort of similar. What am I doing here on both sides? Alpha is a scalar, and then u I have as a vector. On the left hand side, I am first multiplying u by alpha and then applying the t. On the right hand side, I am applying t to u first and then multiplying by alpha. These two should also be the same. If these two conditions are satisfied, then we have a linear transformation. Okay, so basically, if you want to think about it sort of from a high level, what linear transformations do is they preserve addition and scaling on either side of the linear transformation. But from input to output, addition and scaling are sort of preserved in some natural way. So this is what is linear transformation. So let's just quickly go through the previous example. We saw three transformations earlier: translation, scaling, rotation. Okay, I want you to take a moment, maybe pause the video and think about which of these are linear, which of these are non-linear. Okay, so it's some are easy to figure out, some are a little bit more difficult. I'm not going to write it down in great detail for you. I'll let you think about it. The scaling, it turns out, is linear. Okay, so scaling is very easy to show that it's linear. Okay, so let's see why scaling becomes linear. So if you have t of u1 plus u2, it would be alpha times u1 plus u2, which clearly becomes alpha u1 plus alpha u2. And what's alpha u1? T of u1, and then alpha times u1 is t of u1, and then alpha times u2 is t of u2, isn't it? So it's very direct here. And even this one, okay, this already is alpha, maybe this should be some alpha 1 or beta, right? So beta times alpha times beta times u is also the same as alpha times beta times u. So you can see very easily that these two conditions are satisfied. So scaling, it's linear. Okay, so how do you check whether a transformation is linear? You simply take this and apply it here with arbitrary u1, u2 and arbitrary u and alpha. Okay, I put alpha here, but remember this alpha is different from this alpha. You should use something else here. So that if you do that, you should check both these conditions. There's no other way to do linearity, right? So you have to check these two conditions. Okay, remember this is these two definitions are given. You have to check these two conditions. So it turns out rotation is also linear. It's a little bit more complicated to see. I'm not going to prove it. I'll leave it as an exercise. You can put out a solution if you like. Rotation is also a linear operation. If you add two vectors and then rotate, it's the same as rotating the two vectors and adding. Okay, so you try and prove that. And if you scale a vector, maybe scaling is easy to see, right? If you scale a vector and then rotate, you can also rotate and then scale. That's probably easy to prove. But addition maybe is a little bit tricky, but you can prove it. Interestingly, it turns out the translation is not a linear operation. Okay, you can see why that is true. Like for instance, a very simple example is to show something is non-linear. Okay, so there are two different things. To show something is linear, you have to prove these two for every possible u1, u2 and u and alpha. To show something is non-linear, you only have to find one example where this condition is violated. Okay, just one example. Find one u1, one u2 for which the first condition is violated. Okay, you can do that very easily for translation, right? You can take u1 and u2 to both be 0, the origin, right? The 0 vector. If you take u1, u2, 0, what happens in the left hand side? 0 plus 0 is 0. You will have t of 0, which is just the vector ab. But notice what happens on the right hand side. If you put u1 equal to 0, I'm going to get ab here. When you put u2 is equal to 0, I'm going to get another ab here. So while on the left hand side I got just AB, on the right hand side I get AB plus AB, and clearly that is always violated. Okay, so you see the translation, of course, for any non-trivial non-zero translation, it ends up being non-linear. Okay, so I hope you saw these kind of examples. These are once again, remember how to show linear versus non-linear. For proving linear, you have to show that these two conditions hold for every u1, u2 and every u1 alpha. To show that it's non-linear, you have to show just one exception, one case where this doesn't hold, one violation of this condition, and then you'll be done. Okay, so I hope this gives you an impression of this linearity, and it turns out linear transformations are very, very nice and easy to understand, much easier to understand than general transformation. So we'll try to look at that. Okay, so here is the property. Okay, so linear transformations have very many powerful properties. One of the properties they have is, if t is linear, then t of 0 is 0. Okay, so it means a linear transformation will take the origin to itself. It cannot do anything else to origin. So this can also be used as a test for linearity. In fact, translation fails this test, right? Both of these pass this test. You can see translation fails this test. This t of 0 equal to 0 can be used as a property for testing linearity. But even if t of 0 is 0, the transformation can still be non-linear. Okay, so this is not a sufficient condition. This is one of those conditions, one of those properties of a linear transformation. So if this is violated, certainly it's not linear. But if this condition is satisfied, it's not enough for linearity. You have to go back and prove these two properties again. Remember that. How do you prove this t of 0 is 0? Okay, I'll show you a very interesting proof. Let's say t is linear. Then this is true for all u1, u2, no? And you simply put u1 equals u2 equals 0. What should happen here? T of 0 equals t of 0 plus t of 0. One of the t of 0s will cancel, and you will get t of 0 equal to 0. So you can see how just this simple property being satisfied forces you to have t of 0 equal to 0. Okay, so this is a lot of things about linear transformation. You can see the power, right? It's a very simple assumption, and it's very, very useful, and it simplifies the world of linear transformations. Okay, so let me stop here at this point, and we'll pick up the study of linear transformation in more detail in the next lecture.